Welcome to the second session of NMR Spectroscopy of 6th semester DSc 2B, Mysore University, Maharani Science College for Women, Mysore. Contents of this video are shielding and deshielding in NMR, chemical shift and factors influencing chemical shift, measurement of chemical shift, spin-spin coupling or spin-spin splitting. Shielding and deshielding in NMR. In the NMR spectrum of a compound, the electrons around the proton also play their role. When a compound is placed in the magnetic field, the electron around the protons also generate a magnetic field called induced magnetic field. The induced magnetic field may reinforce or oppose the applied magnetic field. These two cases arises. One is if the induced field opposes the applied field, the effective field strength experienced by the protons decreases. Thus, a greater applied field is required for the excitation of protons to higher level than the proton absorbs upfield. The proton is said to be shielded by electrons. Second one is if the induced field reinforces the applied field, an enhanced field strength experienced by the proton, thus a greater applied field is required for the excitation of protons to higher level. Then the proton absorbs downfield. The proton is said to be deshielded by electrons. A smaller field strength will be sufficient for absorption of energy to give NMR signal. Shielding and deshielding by protons is a result of factors like the inductive and electromagnetic effects of groups and hydrogen bonding. Chemical shift. The shift in the NMR signal compared with the standard substance as a result of shielding and deshielding by electrons is referred to as chemical shift. Factors influencing chemical shifts are: one is inductive effect caused by electronegative atoms. Second one is pi electron induced anisotropic effects. Third one is van der Waals deshielding. First one is inductive effect caused by electronegative atoms. Atoms or groups which are electron withdrawing deshield the protons. The effective field strength experienced by the protons in such a case is more than normal. Hence, the proton will absorb downfield. Atoms like halogens, oxygen, nitrogen are electron withdrawing. If such atoms are linked with protons, they shield the proton, resulting in downfield absorption. For example, the chemical shift of CH4 protons and CH3Cl protons can be taken here. Chlorine atom is an electronegative atom that will withdraw the electron density towards itself from the neighborhood of the proton. As a result, the induced magnetic field due to electron circulation around the proton is diminished. Then a smaller applied field is required to cause the proton to flip. Hence, the proton is said to be deshielded and is observed downfield effect. Therefore, the shift will be to higher ppm. In the case of CH4, due to the electron releasing effect of methyl group, the electron density around the proton increases, thus shields it, and therefore the peak appears on the lower ppm side. The electron withdrawing groups reduce the electron density around the proton or deshield the proton, thereby resulting in downfield absorption. Electron releasing groups increase the electron density around the proton, thereby resulting in upfield absorption. Some of the chemical shift values are given below here. For tetramethylsilane, it is 0. For ketones, it will be 2.10. For amines, it will be 2.2. For ethers, 3.3. Dichloromethane, it will be 5.28. Trichloromethane, it will be 7.24. Second one is pi electron induced anisotropic effects. The magnitude of Chemical shift is proportional to the strength of the applied field and is caused by the circulation of surrounding electrons above the protons. When an organic molecule with pi electrons is placed in a magnetic field, an induced magnetic field is obtained due to the circulation of pi electrons. This induced magnetic field is directional, that is, unsymmetrical, and is called anisotropic. The effects of this induced field are called anisotropic effect. These effects are paramagnetic in certain directions and diamagnetic in other directions. Anisotropic effect in alkenes. So in alkene, induced magnetic field will be generated in this direction, which is parallel to the applied magnetic field in the region of these protons. So these protons are deshielded and delta will be more for this. These are called deshielded protons. So delta will be 5.5 to 6 ppm. In the case of alkynes, the induced magnetic field will be in this direction and the applied magnetic field will be in this direction. Applied magnetic field opposes the induced magnetic field in the region of alkyne protons. So these alkyne protons are shielded and delta will be less. They are diamagnetic. You can say diamagnetic. So the delta will be 1.5 to 2.5 ppm. In case of aromatic compounds, the induced magnetic field will be in this direction and the applied magnetic field will be here, and applied magnetic field and induced magnetic field are parallel in the region of aromatic protons. So these protons are deshielded. So delta will be more for this, 7 to 8. Third one is van der Waals deshielding. In a sterically hindered rigid molecules, the electron cloud the hindered proton and hence the proton is deshielded and appear at higher delta values. The shift due to this is quite small. This type of deshielding is observed in highly substituted alkalides and steroids. Measurement of chemical shifts. In order to measure or record chemical shifts, tetramethylsilane is taken as the standard. The choice falls on TMS for the reasons given below. It has 12 equivalent protons and thus gives a sharp signal. Second one is electromagnetic value of silicon is 1.8, which is lower than that of carbon. Consequently, the shielding of equivalent protons in TMS is more than that of almost all organic compounds. Therefore, the signals of almost all organic compounds appear in the downfield direction with respect to TMS. Third one is TMS is chemically inert and possesses a low boiling point of 300 Kelvin. It can be easily evaporated after the experiment to recover the compound. Chemical shifts are expressed in frequency units, cycle per second. There are two scales for expressing chemical shifts. These are delta scale and tau scale. Both of them are in parts per million. This is the delta and tau. Taking the position of TMS, signal is taken as 0 ppm. Most chemical shifts values between 0 to 10. A small value of delta indicates a small downfield shift, whereas a large delta value indicates a large downfield shift. On the tau scale, the position of the TMS signal is taken as 10 and most compounds have chemical shift values between 10 to 0. This is explained with the help of this diagram. This is the TMS signal and this is delta scale and this is tau scale. Shielding effect with upfield shift, deshielding effect with downfield shift. Spin-spin coupling or spin-spin splitting. In a proton spectrum of ethanol, one would expect three specific signals at three specific chemical shifts. One for CH3 group, one for CH2 group, and one for OH group. A typical CH3 group has a shift around 1 ppm. The CH2 group attached to the OH group has the shift of around 4 ppm, and the OH group has the shift around 2 to 3 ppm depending on the solvent used. Interestingly, the shape and size of peaks are indicators of chemical structures too. In the above example, the proton spectrum of ethanol, the CH3 peak would be 3 times as large as OH. Similarly, the CH2 peak would be twice the size of the OH peak, but only 2/3 the size of the CH3 peak. For ethyl alcohol, three precessional frequency signals appear at 1.2 delta to 3.6 delta and 5.4 delta. This indicates that there are three types of protons in ethyl alcohol. The ratio of intensities of the absorption bands are measured by area, and the peaks is the ratio of number of protons in each group. The low resolution spectrum of ethanol shows three peaks in an area ratio of 1:2:3 corresponding to OH, CH2, CH3 groups respectively, as in the figure given below. This is for OH, this is for CH2, this is for CH3. Splitting of spectral lines arises because of coupling interaction between neighboring protons and is related to the number of possible spin orientations that these neighboring protons can adopt. This phenomenon is called spin-spin coupling or spin-spin splitting. In ethyl alcohol for CH3 group, there are three orientations possible due to CH2 group. For two protons of CH2 group, there are four possible orientations due to CH3 group. Thus, the signal splits into quadret. The magnitude of multiplet separation resulting from spin-spin interaction is independent of the strength of the applied field. N+1 rule. This is the simple rule to find the multiplicity of the signal from a group of protons. Count the number of neighboring protons, N, and add 1. Under the high resolution, the peaks of ethyl alcohol appear as multiplets. Peak due to CH3 protons is split into triplet. CH2 protons peak split into quadret. The number of lines observed in NMR signal for a group of protons is not related to the number of protons in that group. It depends on the number of protons in the neighboring groups. This is the NMR spectrum of ethyl alcohol. Singlet for OH. This is quadret for CH2, triplet for CH3. Thank you.